Hello, my name is Dr. Colin Campbell and I'm a research scientist here at Meter Group, and today we're going to talk about thermal time and its association with accuracy. Now, I was really interested in this concept recently because I'm doing some work in a potato crop, and I already knew that a non-aspirated temperature sensor versus an Atmos 41 temperature sensor would be different because the non-aspirated has an accuracy of about 3 degrees and the Atmos 41 has an accuracy of about plus or minus a half a degree. So I was assuming I'd see a difference. But what I wanted to know was, how would that affect the prediction of thermal time? So I just drew up here a graph showing how in the field the non-aspirated temperature sensor here in black compared to the Atmos 41 air temperature measurement. And not surprising, during high thermal load, high solar load time during the day, so this is time on the x-axis and temperature on the y-axis, we do see a difference during that time. What I didn't quite expect, but I saw on some days, was also a little difference in the temperature at the low side too. Now when the sun came up and when the sun went down, what I saw was not a lot of difference, as I've shown here. So the question I had was, considering the temperature difference, what would that do to my thermal time prediction? So I introduced in another chalk top a couple of different ways of measuring thermal time. One was just summing the average minus the base temperature multiplied by the time step, which is a day. And the other would be what I thought was a more accurate way of doing it, where we sum each day the thermal time, but we calculate the thermal time using an integral of the temperature at some time t minus the base temperature. And then we have some time step dt. And that time step is, could be anything, but I wanted to be pretty accurate. So I used 5 minutes in this analysis. So I actually used an integral across the day to sum this in this way. And so I put together just a little table about what I learned there. I wanted to get enough data so that the comparison would be good. Some days there's high solar load, some days there's not. And so basically if I average over a long enough length of time, that comes out in the wash. And essentially this is what I saw. So I just made a very simple table. This is a sum of 1 month worth of day degrees. And here I've used the simple thermal time model. I've noted up here. Here I've used the integral model right here. And what I expected to see was a difference here and probably a difference there. But this is what I learned. So the non-aspirated temperature sensor, we got 410 day degrees here and 425 day degrees here. So there was a difference between the thermal time model and the integral model. But when we went to the more accurate temperature measurement here, what we found was that not only was it different from the non-aspirated, which we expected, not as much as I thought it would be, but there was a large difference. There also was not so much of a difference between the simple thermal time model and the integral model, which really surprised me. I thought our integral model would actually be a much better way to assess thermal time. But we see that they're fairly similar. Still, using a non-aspirated temperature sensor was a concern. We overestimated thermal time. So just to sum up, better accuracy equals better predictions. We can see that. So the Atmos 41 measurements with better accuracy are going to help. And the Atmos 41 as a research grade measurement tool that's also affordable means that you can make these measurements out in the field and not have to worry about over predicting emergence, insect activity, and other things. In the next Chalk Talk, we're going to sit down together and talk about how location also matters where we make this temperature measurement. So I look forward to talking to you then.